Now, in this video, we will proceed our previous lecture in which we discussed the common emitter configuration of an NPN transistor, and from there we tried to understand that how does the amplification take place, and how does the output is out of phase with respect to input. Now, in this video, we'll be talking about transistor amplification factors, or simply we call them as transistor gains. And and we better understand this circuit now. We have input circuit, we have output circuit, and we have input signal, say Vi, and then we have output signal. Now, the very first thing we would like to define for this common emitter configuration is the current gain. So, if we have to define the current gain, we can define it in both the parameters. We can define this current gain in terms of what's called as AC current gain, and then we can define DC current gain. Now, how do we define this AC current gain? So this will be my one here. So what am I interested in is I want to define the current gain. And current gains are of two types. One is AC current gain and another is DC current gain. So for AC current gain, we'll use a symbol beta AC. And how do we define this beta AC? This beta AC is basically defined as the ratio of small change in collector current. So small change in collector current can be symbolized as in collector current can be symbolized as delta IC. So what it says, the definition goes like the ratio between small change in collector current and with respect to or to the small change in base current, so IB. Okay, at constant collector emitter voltage. So for this circuit, we can take that as VCC or VCE. So I will say at constant VCC. Okay, so we have this collector emitter voltage here. Now this is my beta AC. This is the current gain in terms of AC, and we can define DC current gain. Now for DC current gain, we can take the instantaneous values. So that is beta. Okay, so that beta is it is the ratio between the collector current and base current. So this ratio between collector current and base current gives us the measure of DC current gain. Now we can understand that this IC is certainly greater than that of IB. So if IC is greater than IB, what does that mean? That implies this beta DC or beta AC, they are greater than that of 1. And its typical value lies between 15 to 50. So this is our current gain for common emitter configuration of transistor. Now the next important thing that we have to define here is the voltage gain. Now for voltage gain, we have the symbol for voltage gain as AV. Okay, so how do we define this voltage gain? Is AV is it is defined as the ratio between the small change in output voltage, so delta V out, the small change in output voltage to the small change in input voltage. So it has to go like this. When this resistor acts in the mid of the active region. Now the point here is that we have this equation for V out. So V out is VCC minus ICRL, and we can also have an equation for EMF in terms of the input of this circuit. Now, if I will rewrite them, so here is V out is VCC minus ICRC, and for the input circuit, I will have VI using KVL. I will have VI equal to VBB and plus IBRB. So IBRB. Okay, this should be the case. Now, now if I go with this and if I look for the change here, so if I calculate the small change in the output, so what am I going to get here is minus del IC RC. Since this VCC is constant, so its delta will certainly give us 0. So delta V out will be minus delta IC RC, and that should be clear. And for delta VI, similarly, we can have what we will have, that will be delta IB RB. I think, yeah, that's C here. So we have got both the equations. We want to have an expression for voltage gain, and here we can see that this voltage gain AV, it will be delta V out is, this is minus delta IC RC by delta IB RB. All right, so so what we have here, we have the expression for, we can write down this in terms of the magnitude of gain AV. Now what is IC, delta IC by IB? We have already evaluated that, and that is beta AC. So for this I will use beta AC times RC by RB. Now certainly RC and RB, they are a ratio of collector resistance to the base resistance. This RC by RB is resistance gain. So this is resistance gain. So finally we will have the expression for for the voltage gain as AV equal to beta AC times RG, where RG refers to the resistance gain from input to output. So so here we are able to recognize. One should keep in mind that RC is basically RL here, so we can change that RC by RL to have AV, the voltage gain, beta AC times this is RG. Now this RG is the resistance gain, that is the ratio between the load resistance to the base resistance. Now after this, the next thing that we have to do is to have an expression for the power gain. Now in order to have that, so now we'll be talking about the power gain. Power gain, right? And we can easily have the definition for power gain as the ratio between change in output power with respect to the change in input power. So if I represent power gain by say say P, Power. So this power gain will be delta P out divided by delta Pi. So that should be the case. Now the point is, what will be my PO? Because we have the equation for VO. So PO is VOIC, output voltage into the collector current, and this will be IC square times RO. So we can have, for delta PO, we can simply have delta IC square RO. Now RO is understood, this is the load resistance. And similarly for delta PI, we will have VI and IB. This will be the case because the power is the product of voltage and current. And for this situation, we will have this as IB square RI. Okay, so I is basically here RB. That you can keep in mind. So we can write here this delta PI is equal to it's equal to delta IB square RI. So now we can write, so this is our PI and this is our delta P out. So we can write down the power gain here. Now power gain here will be what that will be delta IC by delta IB whole square times RL, because R out is RL divided by RB. So this is beta AC times resistance gain. So this equation gives us the power gain of the amplifier, power gain of the transistor, NPN transistor, in terms of beta, that is the current gain, and the resistance gain. And then after this, we would like to go for transconductance. So this is 5. Now let's go with transconductance. So this transconductance, it has a symbol GM, and we can go with that symbol. And this transconductance, it's defined as, if I write GM here, it's defined as the small change in the output current. So output current is delta IC in our case. Small change in output current that we call as collector current to the corresponding small change in the input voltage. So small change in input voltage, that is delta that's delta VB, right? Okay, so how do I define corresponding small change in the input voltage at constant output voltage, so at constant VCC. So this is the definition of transconductance. So if we want to calculate this transconductance, we can think of GM as delta IC by delta VB times delta IB by delta IB. So here we will have delta IC by delta IB, okay, times delta IB by delta VB, right? Now this is delta IC by delta IB, and this is certainly beta AC, right? So this is beta AC, and this delta IB and delta VB, if we take its reciprocal, that will give us the input resistance. The reciprocal of this thing will give us the input resistance, so I will call this RI. So GM can be, the transconductance is beta AC times Ri. So this is beta AC times, it's not time, sorry, because the reciprocal of this is Ri, so it is beta AC divided by Ri. So finally, I'm going to write here Gm as transconductance, and this transconductance uh, is is beta AC divided by Ri. Now, if I go back to voltage gain, that is beta AC times RL. So I can immediately use this beta AC from this equation into our equation. Then Gm will be, it will be what? Yeah, it will be A AV. It will be AV divided by, yeah, what is this? This is beta, this is beta AC by Ri. So here I'll have GM equal to AV, the voltage gain. That should be like this. And so voltage gain times, not this times, so this, instead of this, I'm using this by R RL. That should be it. Yeah, that should be RL. RL times. So here is GM. Let me check it again. This is GM equals beta AC is this, and this is the reciprocal of input resistance. So this is beta AC by Ri. Now, if we talk about the voltage gain, what is that? Voltage gain is what is voltage gain? How do we define it in terms of beta AC? That is beta AC divided by. So here I am committing the mistake. It is divide by Ri. Okay, so what's going to happen here? I think it's gone something. RL. It's RL. Sorry. All right, so this is RL, so we can have, finally we will come to get this AV. If I want to write AV in terms of GM, that will be transconductance times the RL. So this will be the voltage gain, and we can write this voltage gain in terms of transconductance of this transistor in common emitter configuration. Now we can understand from these equations that the current gain, that the current gain in the common emitter amplifier, it's much more than that of the current gain in common base amplifier, and voltage and power gains in common emitter amplifier are much greater than that of voltage and power gains in common base amplifiers. So this is why this common emitter amplifier is preferred over other common base amplifiers. So if we'll make the calculations based on these equations that we have obtained, we will find that in common emitter mode, the gain is large, the voltage gain is large, the current gain is large, and the power gain is large. And another important thing that I want to talk about here is that if the base region of the transistor is made thicker, so we talked about this base, and we discussed about it. It has to be thin. It has to be thin. But if we make it thick, then IC, the collector current, is going to decrease, and hence the current gain of the transistor will also decrease. So what is important from manufacturing point of view is that this base should be as thin as possible in order to have the better gain.